This is related rates worksheet number 2. Let's look at number 1 here. The radius of a sphere is increasing at a constant rate of 0.04 centimeters per second. The volume of a sphere is provided here in the problem. At the time when the radius of the sphere is 10 centimeters, what is the rate of increase of its volume? So what we can do first with any related rates problem, it's a good idea to start listing out all the information that's given to us in the problem and then start assigning variables or assigning variables to the numbers or values given in the problem. All right, so here the radius is increasing at a rate of 0.04 centimeters. So 0.04 is referring to the rate of change of the radius. So we know that the radius is not just 0.04, it's the dr dt that's going to be 0.04. Okay, a couple of things will hint at that for us. We see the word increase, so radius increasing. Also, centimeters per second. So we know that this number is associated as a rate because centimeters per second can't be just the radius. So in this case, this will be dr dt, the rate of change of radius with respect to time. So dr dt is 0.04 centimeters per second at the time when the radius is 10 centimeters. So we know r is 10. What is the rate of increase of its volume? So we're not looking for v, we're looking for dv dt because we see the word increase or rate of increase, rate of change of volume. So we're looking for dv dt. All right, so let's see what we can do. We are starting with our volume equation. So v is equal to 4/3 pi r cubed. What we can do is we can find the derivative of each variable. So the two variables here are v and r. Notice pi is not a variable. Pi is just a coefficient that along with 4/3 is just attaching itself to in front of this variable r. So let's find the derivative with respect to time. So v, the derivative of v is 1. V to the first power is just 1. But because we're finding the derivative with respect to time, v becomes dv dt. 4/3 pi is just going to attach itself in the beginning. And then really we're just focused on finding the derivative for r cubed. So the derivative for r cubed will be 3r squared dr dt. And then when we bring down the 3 will cancel out with this 3 in the denominator. So we're left with 4 pi r squared dr dt. All right, so now next we can start plugging in information to help us solve for our missing variable. We're trying to find dv dt. So we need to plug in r and we need to plug in dr dt. Well, we know what r is, which is 10 centimeters. We also know what dr dt is, which is 0.04 centimeters per second. So let's make that substitution. R gets replaced with 10. dr dt gets replaced with 0.04. We multiply everything through, and we get 16 pi cubic centimeters per second. So we have to be able to notate the correct unit of measure for dv dt. So dv dt is cubic centimeters. Rate of change with respect to time, so per second. All right, part B. At the time when the volume of the sphere is 36 pi cubic centimeters, what is the rate of increase of the area of a cross-section through the center of the sphere? So if we were to take a sphere and if we were to cut it in half and were to look on the inside of what we just cut, we're going to see that the cross-section is going to be a circle. So if we were to take a ball and cut it in half, the inside, looking inside, we're going to see a shape of circle. So the area of a cross section is talking about, in this case, the area of a circle. Okay, so let's see. Let's list out what we know. We know that at a particular moment in time, our volume is going to be 36 pi. We know that volume is 4/3 pi r cubed. So let's see here. What is the rate of increase of the area? So we're trying to find dA dt, rate of change of area of a circle. We know A is pi r squared. If we go ahead and we find the derivative of A becomes 1, and we attach dA dt. Pi r squared becomes 2 pi r dr dt. And we can start plugging things in here. Well, let's see. We're missing a couple of pieces of information. To find dA dt, we need r and we need dr dt. Okay, So dr dt we can find by it's actually going to be the same. It's a constant rate of 0.04 centimeters per second. So we're going to use that same information here. Okay, so 0.04 is dr dt. The thing that's missing, information that's missing, is going to be r. We don't know what r is, but we do know what the volume at the moment in time is 36 pi. So if we can use the volume equation, we can work through and solve for r. So 36 pi replaces v, and if we can do that, we can solve for r cubed. So what we can do is we can divide both sides by 4/3 pi, so the pi cancels out. 36 divided by 4/3, the same thing as 36 times 3/4. So 36 times 3/4 will give us 27. Take the cube root of r, cube root of 27, which is 3. So we have 3 as the radius, which we can now plug in to therefore find dA dt, which is 0.24 pi square centimeters per second. At the time when the volume and the radius of the sphere are increasing at the same numerical rate, what is the radius? So we're trying to find out, what is the radius when the rate of change of the radius and the rate of change of volume is equal. So what we want to do is we want to figure out when dv dt is equal to dr dt. So we set them equal to each other. So dv dt is, we know, to be 4 pi r squared dr dt, right? We found that from part A here. Well, if we do that, we know that this is the relationship here between dv dt and dr dt. Well, at the moment that dv dt is equal to dr dt, we can replace dv dt with dr dt, because we know that at this particular moment, when dv dt and dr dt are the same, what would be the radius? So if we can just get everything in terms of dr dt, then we can conveniently cancel those out. Just becomes 1. So 1 is equal to 4 pi r squared. Divide both sides by 4 pi, and then take the square root, and we get r, which is square root of 1 over 4 pi, or 1 over 2 square root of pi centimeters. All right, number 2, jet A travels due east from San Francisco. So we have San Francisco in the west, we have St. Louis in the north, and then we have New Orleans in the south. So jet A is traveling from San Francisco towards St. Louis, and then jet B is traveling from New Orleans straight up to destination St. Louis. All right, and the information that's provided here, we see that we're going to have this is going to form a right triangle, the configuration between the 3 cities here. And we can label, I'm going to go ahead and label the horizontal distance between jet A and St. Louis to be x, the vertical distance from jet B to St. Louis as y, and then the distance at any given time between jet A and jet B as the hypotenuse, which is z. Okay, so it says find the rate of change of the distance between the 2 jets. So we're trying to find the rate of change of the distance between the 2 jets. So therefore we're looking for dz dt. Okay. All right, so let's see what happens here. We know the 3 lengths are related to one another by Pythagorean theorem, so we can start off with x squared plus y squared equals z squared. Okay. We know that jet A is traveling due east at 500 miles per hour. So jet A is traveling at 500 miles per hour. However, in relation to what's happening to this length x, as jet A is moving closer towards St. Louis, the distance is going to decrease. So this x, or this horizontal distance of this triangle, is going to keep decreasing over time. So that's why we have to represent dx dt as negative 500, simply because that distance is decreasing. Okay, nothing to do with the direction that this jet is traveling. Okay, what's important is we need to kind of visualize what's happening to the lengths over time. Same with the distance between jet B and St. Louis. We know that as jet B is traveling towards St. Louis, this y distance is going to decrease. So that's why we have to we have to make the adjustment and say that dy dt is negative 600 miles per hour because the distance is decreasing. Distance between jet B and St. Louis is decreasing at a rate of negative 600 miles per hour. Okay? All right, at a moment in time, when x is 100, when z is 300, so jet A is 100 miles from St. Louis, jet B is 300 miles apart, and then if we want to find the distance between jet B and St. Louis, we can go through the Pythagorean theorem, so x squared plus y squared equals z squared, and then we can simply solve for y. I didn't show the work here, but going through the Pythagorean theorem, when we solve for y is roughly 282.843 miles. Now, we should have all the information that we need to plug in after we find the differential equation. So let's find the derivative for each. So x squared becomes 2x dx dt, y squared becomes 2y dy dt, and z squared becomes 2z dz dt. Okay, so now it's just a matter of plugging everything in. We have values for x, y, and z. We have values for dx dt and dy dt. The only variable that's missing is dz dt, and that's what we're looking for. So we just plug everything into our equation, and then we just solve for dz dt, which ends up being negative 732.353 miles per hour. So this negative should make sense because as jet A and jet B gets closer towards their destination, the distance between the two of them are also going to be decreasing. So therefore, that's why that negative is there. All right, number 3. A man is driving north at a rate of 17 meters per second. He sees a railroad track ahead 20 miles ahead of him that is perpendicular to the road. So here, this is the train track here. There is a train going east on the track crossing the road when a man determines with a radar gun that the engine is 35 meters from him, and the distance between his car and the engine is increasing at a rate of 5 meters per second. What is the speed of the train? All right, so the moment that he passes, we can create a right triangle out of that distance. We have the man driving north, we have the railroad track going to the east, and then the distance at any moment in time between the car and the train. So if we think about what's happening to the lengths of this triangle here, we know that as y gets closer towards, we expect that y to be decreasing over time, right? That this x, however, is going to be increasing over time, so we expect that to be a positive value. And let's see here. And then we're told that dz dt, the rate of change between the car and the engine, is increasing at a rate of 5 meters per second. So we know that we can keep this as a positive value. Okay, but we know dy dt must be negative since this distance is decreasing over time. All right. All right. Let's see what we have here. So we know y is going to be 20. So the distance between the man and the railroad track is 20 meters. Z is 35 meters. So distance between the car and the engine is 35. So then we can go through Pythagorean theorem, x squared plus y squared equals z squared, to solve for x, which is 28.723. So now we should have all the information that we need to plug into Pythagorean theorem's differential equation, just like before. And then we go through Pythagorean theorem, and then we start plugging everything in. So x gets plugged in, y gets replaced, z gets replaced, dy dt and dz dt gets replaced, and then the only thing that's missing is now going to be dx dt, which is 17.929 meters per second. Okay, part B, what is the rate at which the area of the triangle is changing? So the area of this triangle, as these moving parts are going along, what is going to happen to this area of the triangle that's formed? So let's think about what the formula for the area of a right triangle is. It's going to be 1/2 base times height. so 1/2 x times y. We want to find dA dt, so to find dA dt, we need to find the derivative. So to find the derivative, notice we have two variables, and these two variables are related to one another by product or by multiplication, so we have to go through product rule. So I'll treat 1/2 x as my f, and then my y as my g. So I just go through product rule, f prime g plus f g prime. And we start going through product rule here. So f prime is 1/2 dx dt times g, which is y, plus f, which is 1/2 x, times g prime. So the derivative for y is dy dt. And then we can start plugging things in. So dx dt gets replaced with 17.929. Y gets replaced with 20. So it's the same scenario as number 3, part A, plus 1/2 x, so x gets replaced with 28.723, dy dt gets replaced with negative 17, and then we just put all this together. dA dt is negative 64.84 meters per second squared.